what will actually happen when our sun dies. Dear traveler, greetings. Today we look up at the star that has ruled our sky for over 4 billion years, a star that warms us, illuminates us, and on which we depend every moment. But like all stars, the sun is not eternal. A day will come when its heart will be exhausted. What will happen on that day? But before embarking on a new adventure, don't forget to like the video and subscribe to the channel so you don't miss anything. Thank you and have a good journey. When you look up at the sky in broad daylight and capture the sunlight, you are actually perceiving the radiation coming from its outer envelope. This layer, called the photosphere, constitutes the luminous region visible to the naked eye. Behind this boundary unfolds a vast space, about 1.5 million kilometers in diameter, dominated by extreme forces and temperatures. Like most stars, the sun is mainly composed of gas and maintains a fragile balance between gravity, which causes it to collapse, and an enormous internal pressure born in its very hot central zone. This harmony is known as hydrostatic equilibrium. This hydrostatic equilibrium is the key to the sun's stability. It relies on a balance between gravity, which pulls matter towards the center, and the pressure generated by the heated and fusing gases. As long as this ratio remains stable, the size of the star does not vary significantly. When the core produces enough energy to balance the weight of the upper layers, the sun maintains its stability. But let's first examine the distribution of the different internal regions, each with its specific role. Let's dive into the very center of the star. The heat there reaches unimaginable temperatures, estimated at several million degrees Celsius. This is where thermonuclear fusion takes place, a process during which hydrogen nuclei fuse to form helium, releasing an immense amount of energy in the form of radiation and heat. This energy, after a long journey through layers of gas, eventually reaches the visible surface. In this central region, the temperature and density are such that particles constantly collide. Fusion produces a large quantity of energy in particles. The radiation, mainly composed of photons, bounces in a very dense medium, which considerably delays its movement outward. It can take several thousand, even tens of thousands of years, before a photon manages to travel from this central zone to the surface. This long journey is explained by the fact that the photon is continuously absorbed and then re-emitted in different directions. This area near the core is called the radiative zone because energy is transferred there mainly by radiation. The density of the material is high and the temperature gradient is significant, making this mode of transfer the most efficient. Energy thus progresses slowly until it reaches the next zone, the convective zone. Moving away from the radiative zone towards the surface, we enter the convective zone. Here, the conditions of density and temperature change. The temperature remains very high, but no longer allows for energy transfer solely by radiation. Convection movements appear similar to those of a boiling pot of water. Huge bubbles of hot gas rise to the surface, release their heat, then descend cooled before heating up again. This circulation creates a dynamic visible in the form of granules, luminous patterns observed in high resolution on the surface of the sun. Their appearance and disappearance over a few minutes testify to this intense convection. The convective zone also generates complex magnetic fields responsible for many solar phenomena, such as spots, flares, or coronal loops. As the density decreases, we approach the visible layer, the photosphere. The photosphere is the thin skin of the sun visible to the naked eye or with suitable instruments. It measures a few hundred kilometers in thickness, although the total diameter of the star exceeds 1,400,000 kilometers. It is the zone where the gas becomes transparent enough to let light escape into space. The temperature reaches about 5,500 degrees Celsius, much less than the millions of the center. For us, it is extreme heat, but this moderate temperature makes the photosphere a privileged place for observation. Sunspots also occur there, cooler areas around 4,000 degrees, which appear dark due to the contrast. These spots indicate intense magnetic activity. Magnetic fields from the convective zone rise to the surface, forming loops and complex structures, causing local variations in temperature and brightness. Above the photosphere are the chromosphere and the corona, very thin and tenuous layers. There, temperatures rise to several million degrees due to the magnetic fields. Nevertheless, our focus remains on the current state of the Sun and its main layers, with the photosphere being particularly noted as the luminous boundary that diffuses the light reaching us. Now that the internal structure is clear, let's return to hydrostatic equilibrium, which prevents the Sun from collapsing or exploding. As long as hydrogen fusion into helium continues in the core, the internal pressure counterbalances gravity. The Sun remains stable in the main sequence for over 4 billion years. It is about halfway through this phase, with no imminent signs of extreme aging from our perspective, despite continually evolving on a geological scale. Meanwhile, the Sun's surface and magnetic field are constantly evolving. Approximately every 11 years, a magnetic cycle dictates its activity. During this period, the number of sunspots fluctuates. The term solar maximum is used when magnetic fields are intertwined at their peak, and solar minimum when they calm and are more organized. This cycle influences not only the visible aspect of the photosphere, but also the entire solar activity: eruptions, solar wind intensity, flux of charged particles spreading through interplanetary space, and even the conditions of the space climate around Earth. This magnetic phenomenon stems from an internal mechanism known as the dynamo effect, linked to the movements of conductive fluids in the convective zone. About 4.6 billion years ago, a cloud of gas and dust collapsed under the influence of gravity in a region of the Milky Way. Most of this material formed the core of our star, while the rest organized into a protoplanetary disk, from which planets, comets, and asteroids emerged. At that time, the initial chemical composition was mainly hydrogen and helium, with a small proportion of heavier elements, called metals in astrophysics. This term even includes elements like carbon, nitrogen, or oxygen, as opposed to the two main light gases. Today, the Sun is still predominantly composed of hydrogen and helium, but its composition has slightly evolved. Each fusion of hydrogen in its core produces helium, gradually modifying internal proportions. Furthermore, fusion, the influx of interstellar matter, and solar wind exchanges affect its surface. However, the most significant changes will occur later, when the Sun begins to lose mass at the end of its life. Currently, its structure remains relatively stable, with a helium-enriched core, while the surface retains a composition close to the original. Since its formation, the Sun has traversed the galaxy in rotation, encountering various gas clouds and undergoing large-scale stellar influences. These interactions have altered its metallicity, which is the proportion of elements heavier than helium. Each generation of stars slowly enriches the galaxy with metals through supernovas or other stellar end-of-life phenomena. The Sun, originating from an already enriched generation, presents medium to high metallicity, favoring the formation of rocky bodies in the inner zone where Earth formed. In sum, without this metallic content, our planet might not have been born. Beyond the light and heat essential to terrestrial life, the sun is crucial to the dynamic stability of the solar system. This stability means it keeps the planets on stable and predictable orbits. Its mass represents more than 99% of the total mass of the solar system, including planets, asteroids, comets, and other small bodies. This mass creates a central gravitational well around which the planets have revolved for billions of years. Solar gravity holds the planets according to their orbital speed and the distance separating them from the sun. During the formation of the solar system, major upheavals affected the orbits. The giant planets, such as Jupiter and Saturn, played a significant role in these migrations, ejecting some small bodies towards the exterior or interior of the system. Over time, a balance was established, leading to the current configuration. Without this stable gravitational center, the ordered structure of the planets would be impossible. The sun also acts through its magnetic activity and solar wind. The latter, a continuous flow of charged particles, forms a bubble called the heliosphere, which partially protects the solar system from cosmic rays. It also influences the formation of comet tails and can affect planetary atmospheres, induce polar auroras, and disrupt radio communications during major eruptions. Thus, the sun is not just a simple emitter of light. It is a major actor in all gravitational, thermal, electromagnetic, and radiative interactions that orchestrate the ballet of celestial objects. Without it, there would be no light, no heat, no planetary stability. It is the cornerstone of our solar system. About 4,500 million years from now, a key moment in the future history of the sun will occur. At this stage, the hydrogen that has long fueled the fusion in the heart of our star will be almost exhausted. This situation will lead to a series of profound transformations within the sun, altering its radiation, structure, and, consequently, the living conditions in the solar system. As soon as the core no longer has enough hydrogen to maintain the same rate of fusion, the internal mechanism will reorganize to continue its energy production. The study of similar stars allows us to predict a readjustment of the balance between gravity and pressure in the central region. The core will gradually contract, while a fusion shell around it will become more active. This change, though slow on a human scale, will be enough to cause an approximately 10% increase in solar luminosity per billion years, deeply modifying Earth's climate. Since its formation about 4,600 million years ago, the sun has maintained a delicate balance between two forces, gravity, which pulls matter toward the center, and the pressure from the nuclear reactions in the core, which push it outward. Today, this balance is stable thanks to the fusion of hydrogen into helium, providing the necessary pressure to support the upper layers. This balance will persist for hundreds of millions of years more, but it is not eternal. Over time, the central hydrogen diminishes, replaced by helium. When the remaining amount is no longer sufficient to maintain the fusion pace, energy production will drop, causing an imbalance that will initiate core contraction. Gravity will temporarily prevail over fusion pressure, the central temperature will rise, and the compressed matter will become hotter and denser. This temperature increase will shift the fusion to a shell-like region surrounding the hydrogen-depleted core. This shell will become the primary energy source, burning the remaining hydrogen at a rapid pace. Subjected to extreme pressures and temperatures, it will produce intense energy, amplified by the central contraction that facilitates transfer to the surface. The sun will then radiate more, its luminosity slowly increasing by about 10% per billion years. A figure that, although modest in appearance, will suffice to destabilize the thermal equilibrium of nearby planets. Earth, particularly sensitive to solar irradiance, will undergo a gradual rise in its average temperature. Even an increase of a few percent in luminosity, accumulated over hundreds of millions of years, could warm the planet by several degrees, disrupting atmospheric circulation, precipitation distribution, and the dynamics of ice caps. Climate models indicate that the habitable zone of the solar system will slowly move outward. Earth's oceans, essential climate regulators, will evaporate more rapidly, enhancing the greenhouse effect and accelerating warming. This process will make the planet progressively less conducive to life as we know it. Today, the sun regulates its stability through a natural adjustment. If fusion produces more heat, the central region expands, reducing the temperature and slowing down fusion. If it weakens, a slight contraction increases pressure and temperature, restarting the reaction. When the central hydrogen is depleted, this mechanism will alter. A core primarily composed of helium, unable to fuse effectively, will change the internal dynamics. Shell fusion will take over, but with less stability, making the star more sensitive to internal variations. The first imbalances will appear imperceptible on a human lifetime scale, but real. In reality, the sun is structured in distinct zones: a core where fusion occurs, a radiative zone, and closer to the surface, a convective zone. Today, the boundary between these zones remains stable, but when the core contracts and fusion moves to the shell, an inert helium core will form, energetically inactive, while the shell burns intensely. This reorganization will change the heat distribution, affecting the size and role of the radiative and convective zones. The luminosity will increase because this shell, subjected to extreme pressure and temperature, will temporarily produce more energy than the initial core. The high density of the enriched helium core will favor the burning of residual hydrogen. Although gradual, the energy surplus will accumulate and result in an increasing illumination of the planets. This process will occur in small steps, each lasting tens of millions of years, but its climatic effects on Earth will be cumulatively spectacular. This evolution will be accompanied by internal changes on Earth. Plate tectonics, the carbon cycle, the release of volcanic gases, or the formation of carbonate rocks will react to the new conditions. The more the planet warms, the more the evaporation of surface waters will increase, along with the concentration of water vapor, a potent greenhouse gas. This mechanism will amplify warming over scales of tens or hundreds of millions of years, a brief period on a geological scale, but with significant consequences for the future of our world. While the core of the sun is depleted of hydrogen, other subtle processes are set in motion. Regarding fusion reactions, we mentioned the gradual appearance of an active shell around the core. But how do we know the core is losing its hydrogen? Scientists use multiple approaches, observing aging stars in the galaxy whose light and spectrum reveal a depleted core, and numerical simulations integrating nuclear physics, gravity, and energy transport, capable of predicting the evolution of stars comparable to the sun. These studies show that stable hydrogen fusion at the center lasts about 10 billion years before shell fusion takes over. As our star has already covered half of this cycle, it is estimated that in about 4,500 million years, it will enter this phase. Its luminosity, already slightly increased, will continue to rise by about 10% every billion years. For Earth, such a cumulative increase over 1 billion years or more will mean a radical transformation: rising temperatures, accelerated erosion of continents, upheaval of oceanic chemistry, and shifting temperate zones towards the poles. Some studies suggest that the shift towards an overheated and possibly uninhabitable world could occur well before the Sun, having become larger, engulfs our planet. Thus, the fate of the biosphere will depend directly on this gradual increase in luminosity. At the core of the Sun, fusion arises from the combination of hydrogen atoms under extreme temperatures and pressures. When hydrogen becomes scarce, helium accumulates, and gravity compresses the matter further, increasing the temperature even more. Central energy production decreases, and the fusion shell just around the core takes over. The core contracts, concentrating helium at the center and preparing for the next stage of helium fusion in a more chaotic context. For now, our focus is on this transition, where the shell becomes the main energy source. The decline of hydrogen is the first major sign of a sun entering an advanced maturity. The self-regulation is deteriorating. The shell does not offer the fine regulation of the core. Like a campfire fed from the periphery due to the lack of central wood, the sun continues to burn, but with less uniform intensity. The heat now comes from a shell surrounding an almost inert helium core, and slight local variations may appear, even if the overall luminosity follows a slow upward curve. Moreover, some clues could come from magnetic activity. Today, the Sun experiences regular cycles of about 11 years, linked to its differential rotation and the dynamics of the convective zone. As the internal structure evolves towards shell fusion, the magnetic conditions should slowly change. Stellar dynamo models suggest that changes in internal rotation could influence the distribution and intensity of magnetic fields. These variations, imperceptible on a human scale, would nonetheless reveal a profound transformation. Thus, the decline of central hydrogen is accompanied by thermal, structural, and magnetic changes. The gradual increase in luminosity is one of the best established facts in astrophysics, even if Earth's and life's exact reactions remain uncertain. It is not an imminent event, but on a cosmic scale, a few 100 million or 1 billion years represent a near future. This moment will mark the exit from the stable sequence of central fusion and the entry into a path towards more complex nuclear phases. This transition, although slow, could make Earth's conditions very hostile. Models indicate that in a few 100 million years, a moist greenhouse effect could set in. Water vapor would accumulate in the atmosphere, the stratosphere would become laden, and hydrogen would escape into space, gradually drying out the planet. The habitable zone, today favorable to Earth, will slowly move outward. Long before the Sun swells significantly, Earth could already resemble a burning and dry Venus. This phenomenon does not only concern Earth. In the long run, all the planets will feel the effects of the increasing luminosity, even if distant worlds like Jupiter or Saturn will be less affected. For our planet, whose climate depends directly on solar radiation, a variation of a few percent is enough, in the long term, to transform habitability. The ignition of the fusion shell already prepares the next stage of the Sun's life, the burning of helium. This adaptation illustrates the ability of stars to exploit each fuel reserve, even if it means upsetting their internal balance. In the case of the Sun, the outcome is clear: a continuous increase in luminosity, with a growing impact on nearby planets. The depletion of hydrogen is the herald of an even more radical transformation. In this cycle, everything begins with the decrease of central hydrogen, leading to a contraction of the core, then a rise in temperature and density in the shell, intensifying fusion. This increased energy production makes the star brighter. On Earth, this additional energy, negligible over a century, but decisive over 1,000,000 years, will gradually disrupt the climate and ocean equilibrium, reducing the chances of survival for the biosphere. It's the gradual exit from the green zone, which ensures today a stable and tempered sun. In approximately 5,400,000,000 years, our sun will begin a slow metamorphosis that will mark the entry into what astronomers call the subgiant phase. At that precise moment, the internal balance of this star, so familiar to our eyes, will begin to deeply transform. At the heart of the sun, the reserve of hydrogen intended for nuclear fusion will dwindle, creating a subtle imbalance between gravity, which tends to contract the matter, and the outward pressure produced by fusion in the layers just above the core. As the core contracts, the outer envelope will expand, resulting in a progressive increase in the overall size of the star. During this period, the solar radius will reach about twice its current value, a dramatic change from the stable and familiar size we know. For a distant observer, this growth will be accompanied by a measurable decrease in surface temperature. This lower temperature, compared to today's, will be the result of the general expansion. The energy produced in the fusion zone will now spread over a larger stellar surface. Seen from afar, the star might adopt a slightly more orangish hue, a sign of the temperature difference in its outer layers. In the core of the star, the central region where most of the solar mass is concentrated, density and temperature will remain very high, but the configuration of fusion reactions will gradually evolve. The amount of hydrogen available at the center will be nearly exhausted, so that the main fusion will shift to a shell surrounding the core. This new arrangement will cause an imbalance. The contraction at the center will raise the temperature, while fusion in the shell will partially support the outward pressure. This dual effect will explain why, despite a denser core, the outer layers of the star will swell and cool slightly. The combination of this internal contraction and this external expansion characterizes the subgiant phase, a crucial stage between the sun's past stability and a future where it will become much larger and brighter. As the envelope of the sun expands, the convective zone, where matter is churned and transported directly to the surface by convection, will move towards the upper layers. Today, the energy produced at the center first traverses a vast radiative zone. Then, further from the core, convection takes over in the outer layer. In the subgiant phase, this convective zone will occupy a larger volume, more efficiently churning the matter and redistributing heat and chemical elements towards the surface. This increased mixing could alter certain spectral signatures observable from a distance, revealing more elements hitherto buried in deeper layers. The most striking consequence of this evolution will be an upheaval in the distribution of heat within the solar system. Without yet becoming a giant, the sun will see its luminosity increase. According to calculations, its brightness could exceed that of its current stable phase, which will enhance the amount of energy received by the inner planets. Long before this stage, Earth will have already felt the effects of the sun's progressively increasing brightness, but the entry into the subgiant phase will significantly accentuate this process. Even a modest rise in the received flux will be enough to disrupt the delicate balance that currently maintains Earth's climate. The notion of a habitable zone will then take on another dimension. Currently located between the orbits of Venus and Mars, This region conducive to the presence of liquid water will move outward with the increase in luminosity. Approximately 5,400,000,000 years into the future, it could be near Mars's orbit, or even beyond. Earth, located about 150 million kilometers from the Sun, will then find itself at the edge, or even outside of this favorable zone. Long before being doomed by a later phase, our planet will undergo an uncontrollable greenhouse effect, rendering its climate far too hot to maintain a biosphere similar to the one we know. The increase in solar flux will likely trigger a series of reactions in Earth's atmosphere. The oceans will warm, evaporation will accelerate, and water vapor will enhance the greenhouse effect, leading to a further rise in temperature. Eventually, liquid water will almost entirely disappear, evaporating into the atmosphere or escaping into space. This transformation will mark the end of most forms of life dependent on surface water. A few extremophiles might survive for a while, but the current ecosystem would be irrevocably disrupted. This shift of the habitable zone to Mars will be of particular importance for the red planet. Although its surface is dry today, it retains ice reserves in its subsurface. The surplus energy received could warm its surface, sublimating more water or carbon dioxide ice. Atmospheric or geological activity could result, bringing Mars closer to more favorable conditions, at least temporarily. However, there is no guarantee that this additional heat could create a thick atmosphere capable of retaining heat long enough to allow the sustained presence of liquid water. And this phase would not last indefinitely. Moreover, solar expansion could be accompanied by changes in the magnetic structure of the star and in the intensity of its stellar wind. This wind, composed of charged particles, influences planetary atmospheres and radiation belts. A more intense or modified wind could accelerate the atmospheric loss of planets with little protection, like Mars. Thus, even if it were in the habitable zone, the red planet might not fully benefit from this climatic opportunity. For Earth, the situation would then be critical. Closer to the Sun than the new habitable zone, it would receive an excess of energy, making it uninhabitable. The ice caps would have long since disappeared, the oceans would be in advanced evaporation, and surface temperatures could exceed 100 degrees Celsius. No region, neither mountain nor pole, would provide refuge. Ecosystems would be profoundly altered, if not non-existent for complex life forms. Scientists estimate that at these temperatures, still poorly understood geological processes could be triggered, such as the partial melting of certain rocks and the massive release of gases. The minerals in the Earth's crust could transform, reacting with the atmosphere and further altering the climate. Gradually, the oceans would boil and then almost entirely evaporate, leaving an arid and irradiated world. The last forms of life would be microscopic, buried underground, or isolated in rare, less exposed areas. This is the very long-term fate that awaits our planet when the Sun begins this irreversible expansion. Nevertheless, the subgiant phase is only a preparatory stage, a gradual transition to a more imposing stellar diameter. During this time, the Sun will not yet possess the considerable dimensions of later phases. Its radius, about twice the current size, will remain modest compared to what is to come. However, for Earth's climate and life, this will already be a major turning point. The delicate balance that maintains moderate temperatures on our planet will be broken, triggering a chain reaction of disturbances that neither biological evolution nor geological dynamics can counter in the long run. This change, imperceptible on a human scale, will put an end, on an astronomical scale, to the long reign of stability that has lasted billions of years. From an astrophysical point of view, the subgiant phase can be seen as the Sun's direct response to the gradual depletion of its central fuel. As long as hydrogen dominated the core of the star, fusion in the deepest zone ensured a lasting stability, maintained by the balance between gravity and pressure from fusion. When the core changed composition and hydrogen became scarce, this balance wavered. The contraction of the core intensified fusion in the surrounding shell, providing the energy needed to swell the outer layers while maintaining some resistance to gravity. This internal adjustment translates on a large scale to the expansion of the outer layers and the modification of the surface temperature. Even during this phase, the Sun will continue to illuminate the entire solar system. The giant planets and their moons will receive a slightly increased light flux, which could alter the chemical alchemy of some icy moons like Europa or Enceladus. However, the most dramatic changes will occur later, when the star reaches even larger dimensions. The subgiant will nonetheless inaugurate a gradual reorganization of thermal and orbital balances. Subtle adjustments in the distribution of mass and the solar gravitational field could, over the ages, alter some orbital resonances while preserving the general stability until the more extreme phases. For Earth, this period will herald an irreversible decline of the ideal conditions that have allowed life for more than 4 billion years. The surface will be driven to temperatures such that no complex organism can survive without protection. Simulations predict a stratosphere saturated with water vapor, leading to an increased loss of this resource into space. The planet will transform into an arid world, subject to a self-sustaining greenhouse effect, where every trace of moisture will be vital for any surviving microorganisms. The overheated upper atmosphere could partially ionize and lose a significant fraction of its light elements, accelerating the erosion of the biosphere. Long before officially entering this phase, life will have already retracted into extreme refuges, buried underground or in the great ocean depths. Extremophile organisms will be the last vestiges of a world whose surface will have become uninhabitable. Photosynthetic ecosystems, which thrived thanks to sunlight, will gradually disappear under the effect of increased heat and radiation. Even an advanced civilization would have very few means to counter the natural evolution of a star at the end of central hydrogen combustion. The energies involved and the fusion processes would exceed any conceivable technology. Migrating to other planets or stellar systems would remain a colossal and uncertain venture. The subgiant phase remains an essential preamble to a far more radical transformation. For now, the Sun still has several billion years of relative stability before this transition, but its internal evolution will inexorably lead it to this state, which will mark the lasting end of conditions conducive to life on Earth. This process is normal. Intermediate mass stars all experience a period of progressive growth at the end of central hydrogen fusion. Long in our eyes, it represents only a brief sequence of their existence on the scale of the universe. If humanity wanted to face this great turning point, it would need to consider exploring other star systems or colonizing the furthest regions of the solar system, where conditions will remain temporarily more favorable. Mars might benefit from increased sunlight, while the Earth would become uninhabitable. But these scenarios remain speculative. Adapting a complex biosphere to such conditions would pose immense challenges. What is certain is that the increase in brightness and atmospheric feedbacks will doom the planet to a geological and climatic furnace, while the gas giants will undergo less dramatic internal transformations. When the Sun reaches approximately 5,400,000,000 additional years, it will have long been engaged in this stage. Fusion will no longer occur at the center, but in a shell surrounding a dense core. This structure will release enough energy to maintain the star at the cost of external expansion, a decrease in surface temperature, and a modification of the convective zone. The Earth, now outside the habitable zone, shifted towards Mars's orbit, will see its seas disappear, its continents become arid, and all surface life either go extinct or take refuge in protected environments. The subgiant phase, often considered merely a transition, will have profound repercussions on the solar system. With a doubled radius, a larger but cooler photosphere, and increased luminosity, the Sun will permanently alter the thermal balance of the planets. This stage, initiated by the depletion of central hydrogen and the ensuing internal reorganization, will move the Earth out of any habitable zone long before the most spectacular transformations to come. It is an inevitable step in cosmic history. Even stars with millennial reigns eventually disrupt their environment before entering more extreme evolutionary phases. Here we are transported 5.9 billion years into the future, to the moment when the Sun embarks on a decisive stage of its existence. By that time, our star will have already exhausted much of the hydrogen at its center, altering the balance that maintained its internal structure. As this reserve diminishes, energy will now come from the fusion of hydrogen in peripheral layers surrounding a helium-saturated core. Due to this shift in production, the Sun's external envelope expands, and the internal temperature reorganizes. This marks the beginning of the vast phase of the red giant branch. This transformation will turn our peaceful daytime star into a reddish colossus, visible from the remaining planets if they still exist in their new orbits. To understand the origin of this spectacular expansion, we must remember that when the hydrogen at the center of a star, similar to the Sun, runs out, the energy source shifts to a shell surrounding the core. Fusion no longer occurs at the heart, but in a shell of hydrogen around the helium core. By contracting under its own weight, this core releases even more heat, which is transmitted to the layers where fusion continues. On the surface, the effects are considerable. The Sun's exterior gradually expands, and its temperature drops. As the energy produced is distributed over a larger area, the surface cools, giving the star the reddish hue characteristic of red giants. For several 100 million years, its radius will reach about 100 times its current size, enough to completely submerge the orbit of Mercury, and very likely that of Venus. The almost certain engulfment of these two planets is explained by the inexorable advance of the solar envelope into the inner regions of the solar system. One might think that Earth, being further away, would escape this fate. However, several factors come into play. During this phase, the Sun will lose mass by emitting a much more intense stellar wind, expelling particles and heavy atoms. This loss reduces its gravity, allowing the planetary orbits to move outward, a phenomenon known as orbital migration, due to stellar mass loss. According to some estimates, this recession could be enough to keep Earth out of reach. But for Mercury and Venus, which are too close, this orbital expansion would not offset the advance of the solar envelope. This intensified stellar wind is a central element of the red giant story. It is a continuous flow of protons, electrons, and heavy elements stripped from the external envelope. Increasing instability and deep convection lead to the rise and expulsion of these elements into space. Less bound by gravity, the matter escapes more easily, causing both a spatial extension of the star and a lightening of its mass, altering the gravitational balances of the planets. Survivors, such as Earth or Mars, will see their trajectory widen over these adjustments. This mass loss is accompanied by variations in luminosity, a consequence of internal instability. The competition between the core's contraction and the expansion of the upper layers leads to cycles of moderate increase and decrease. A temporary energy surplus from the fusion shell inflates the star and increases its radiation, before a weakening causes a slight retraction. For a distant observer, this phase would be punctuated by perceptible luminous pulsations, without reaching the violence of stellar explosions. At the heart of the Sun, helium accumulates in a state known as degenerate, where the extreme density requires electrons to conform to the laws of quantum physics. The Pauli exclusion principle prohibits them from certain energetic configurations, providing the core with additional support against collapse. Despite temperatures of several tens of millions of degrees, the degeneracy pressure stabilizes this region until a critical mass of helium triggers fusion and the future helium flash. For now, we remain in the first great expansion, the core thickening its helium reserve while the hydrogen shell supports the whole. Simultaneously, the convective zone extends in depth. This vertical mixing of ionized gas transports energy from the fusion shell to the surface and alters the visible chemical composition. Heavy elements can be brought up to the photosphere, enriching the emitted light with novel chemical signatures. A close observation of such a red giant would reveal a surface more complex than the one we know today. In terms of time, this transformation occurs over several hundred million years. For a human civilization, it would represent a catastrophe unfolding over tens of millions of years. But on an astronomical scale, this duration remains brief. It still leaves time for orbital migrations, intensification of stellar winds, and the engulfment of the inner planets before the onset of helium fusion. During this period, the Sun's total luminosity will continue to grow, pushing the habitable zone farther out. Long before the envelope reaches the Earth, the increase in radiation and the enhanced greenhouse effect would render our planet uninhabitable. As the Sun loses mass through its stellar winds, the intensity of its attraction on the planets weakens, causing a slight distancing of their trajectories. This dynamic remains complex because, simultaneously, the outer layers of the Sun continue to expand. For Mercury and Venus, this respite will be brief. The reddish swelling, combined with insufficient orbital adjustment to push them far enough away, will seal their fate. Numerical simulations conducted by various teams indicate that Mercury will quickly disappear, followed closely by Venus, engulfed in the gaseous layers. According to some estimates, the stellar envelope could reach, or even surpass, the former Earth's orbit, although the exact extent depends on the rates of mass loss and our planet's orbital reaction. Inside the red giant, the circulation of gases and convective currents reach such intensity that they generate cyclical instabilities, altering brightness and heat transport. These instabilities, termed semi-regular pulsations, vary widely in period and amplitude. Modest contractions and expansions of the envelope are accompanied by variations in the hydrogen fusion zone, leading to temporary luminosity fluctuations. Any evolved life form, if it existed nearby at that time, would see a sky oscillating between different intensity levels, dominated by a vast reddish disk covering a large portion of the horizon. This spectacle would unfold slowly on a human scale, but rapidly on a geological scale, with a certain destructive impact. As the star progresses in this red giant branch, hydrogen fusion feeds a shell surrounding a growing helium core. The end of this first phase is known as the tip of the red giant branch, the moment when the compact core reaches a critical threshold of temperature and pressure, maintained by degeneracy pressure. Helium, more challenging to fuse than hydrogen due to its double nuclear charge, requires extreme conditions. As long as these conditions are not met, the fusion remains blocked, even if the temperature exceeds hundreds of millions of degrees. During this period, the convective zone can dive deeper, promoting internal mixing known as convective dredge-up. These processes alter the composition of the envelope and enrich the red giant spectrum. The expanding surface, though cooler than it is today, still appears scorching to our eyes, reaching several thousand degrees. Its red hue comes from this lower temperature, but its overall brightness remains much more intense due to the immensely enlarged emission surface. Viewed up close, this titanic sphere would glow faintly, occupying a colossal space in the sky. Computer models estimate that this phase of the red giant branch could last several 100 million years until a more sudden event occurs. During most of this period, the helium core remains compressed, close to ignition, while the star expels stellar winds thousands to 1,000,000 times more intense than today. Each pulsation accentuates the mass loss, altering the internal structure and remaining orbital balances. When the core reaches the necessary conditions, it will engage in an explosive reaction. The red giant branch will give way to a new spectacular act. The central point is the extent of the initial swelling. At this stage, the solar radius reaches nearly 100 times its current size. It is then that the engulfment of Mercury and Venus becomes highly probable. The stellar winds, by reshaping the circumstellar dust and orbits, redesign the solar system. Luminosity oscillations reflect the increasing internal unrest, while the core, saturated with helium, approaches its next critical stage. These upheavals also serve as a valuable reference for the study of exoplanets. Understanding how a star transforms the environment of its planets sheds light on the fate of similar systems. In about 6 billion years, our Sun will have become a vast and formidable star, offering only from a great distance a bearable display. The remaining planets will bathe in altered radiation, their habitable zones shifted to more distant regions. The landscapes and rocky cores will bear the irreversible imprint of this metamorphosis. For the astrophysicist, it will be a natural laboratory of invaluable worth. On the chemical level, deep convection brings to the surface elements forged in the internal layers, carbon, nitrogen, and other fusion products. These elements, partially expelled by the stellar wind, enrich the interstellar medium. Although later phases release more heavy elements, this initial expansion already contributes to recycling matter. Astronomers, observing other red giants, witness this process directly, essential for understanding planetary formation and the possible emergence of life elsewhere. Approaching the peak of the branch, the helium core becomes so compressed that degeneracy pressure becomes the main support against gravity. This condition prepares the future onset of the helium fusion flash. In the meantime, the star oscillates, swells, and loses mass. The thermal pulsations and intense convection orchestrate an internal ballet of spectacular magnitude. During these hundreds of millions of years, the solar system, reduced after the disappearance of its first planets, witnesses this monumental transformation. Each celestial body becomes an ephemeral witness to this tranquil fury. During this critical stage, which occurs about 6 billion years from our time, the Sun undergoes a spectacular phenomenon, the helium flash. To understand this term, one must first know that at this stage, its core is essentially composed of helium. Resulting from the previous fusion of hydrogen, this element accumulates gradually at the center, drawn by gravity, unable to fuse until the temperature is sufficiently high. This region of helium, having become extremely dense, is then in a state qualified as degenerate. In this configuration, the matter is in the form of a plasma of electrons and closely packed nuclei, such that the classical laws of gases are no longer sufficient to describe the pressure. This pressure, dictated by the quantum exclusion principle, remains almost constant even if the temperature increases, as the electrons cannot be compressed further. In normal circumstances, in a non-degenerate core, a rise in temperature leads to an increase in pressure, causing an expansion that stabilizes fusion. But here, the density is such that the heat cannot dilate the structure. The particles, confined in an infinitesimal volume, prevent any notable swelling. Thus, when fusion begins, the temperature rises rapidly without the usual regulatory mechanism being able to act. At this stage of its evolution, the Sun has already ballooned and consumed almost all its central hydrogen. Deeply buried in the core lies a vast reservoir of helium. Gravitational contraction and layered fusion around this core gradually raise the internal temperature. The pressure is maintained, while the helium at the center waits to reach the conditions required to transform into carbon. It takes tens of millions of degrees for helium fusion to begin, known as the triple alpha reaction, which combines 3 helium nuclei, or alpha particles, to form a carbon nucleus. The trigger occurs when this already burning and heavily compressed core reaches the necessary temperature for triple alpha fusion. The degeneracy preventing immediate expansion causes the heat to skyrocket. During this brief phase, lasting from a few minutes to several hours according to estimates, the reaction goes out of control and releases colossal energy. This event is often described as explosive, but for a star like the Sun, it does not produce an external manifestation comparable to a supernova. The energy is absorbed by the thick envelope of hydrogen and helium, which cushions the shock and prevents any visible shockwave. The star does not disassemble. It rather reorganizes its internal structure in response to this sudden energy release. In the triple alpha fusion, 2 helium nuclei first unite to form an unstable beryllium nucleus, which, by quickly capturing a 3rd helium nucleus, becomes a carbon atom. This reaction requires extreme temperatures and densities to overcome the electrical repulsion between positive nuclei. It releases a large amount of energy, as the mass of the formed carbon is slightly less than the sum of the initial masses, with the difference being converted into energy. In this degenerate core, the reaction occurs at a dizzying pace, producing a power that can, briefly, exceed the Sun's usual brightness by several orders of magnitude. Yet, the stellar envelope absorbs this flow and slightly expands, dissipating part of the energy. This event marks a profound internal reorganization. The energy released further raises the temperature, reducing degeneracy in the central areas. Thermal pressure then takes over, allowing the core to expand and stabilize helium fusion, which then continues more regularly. This stabilization, although rapid, profoundly changes the internal structure. The star, whose envelope had previously expanded greatly, sees its overall radius decrease, while its surface temperature increases. Its color then evolves toward whiter or bluish hues in the Hertzsprung-Russell diagram, which classifies stars according to their brightness and temperature. Once the flash has passed, the core becomes a stable helium fusion reactor. The excess energy has expanded the internal layers, maintaining the necessary thermal pressure for continued fusion. This stage, called the horizontal branch, is characterized by regular production of carbon and sometimes oxygen, depending on the temperature. During the flash, the sudden increase in energy remains confined to the core. The envelope may slightly quiver, but nothing comparable to a supernova explosion. For the Sun, this episode resembles an invisible fireworks display, perceptible only through the gradual adjustment of its size and brightness. Helium fusion then continues for hundreds of millions of years. The core, less dense than before, has left the extreme degeneracy state and adopts a more classical balance. The contraction of the radius may seem paradoxical, but it is explained by the internal reorganization. The envelope, previously highly expanded, now receives a stable energy flow that allows for an equilibrium in a more compact configuration. From the outside, one observes a hotter photosphere, typical of the horizontal branch, a reduced radius, a higher temperature, and a luminosity variable according to mass and composition. Finally, it is important to recall the brevity of the flash itself. Although the helium fusion lasts for hundreds of millions of years, this sudden surge of energy persists only for a few minutes or hours. Invisible from the outside, it can only be understood through astrophysical modeling. In these extreme conditions, matter adopts a state very far from that observed on Earth. The nuclei float in an ocean of free electrons, and the density reaches billions of kilograms per cubic meter. During this event, the energy released can reach several million times the initial luminosity of the star, although these figures depend on numerical models. The immediate effect on the envelope is to slightly accelerate its expansion and redistribute the internal heat. Then, as the core relaxes, energy production slows down, and the star, less swollen than before this episode, reaches a new equilibrium. It is useful to recall the notion of effective temperature, corresponding to the surface temperature. After the flash, it settles into a higher range than in the pre-flash phase, potentially increasing by 1 to 2,000 degrees Celsius depending on the mass, chemical composition, and internal dynamics of the star. This critical fusion point marks the end of a long phase, during which the helium core was only heating up and compressing. After the flash, helium burns at a regular rate, placing the star in a more stable regime, called the horizontal branch on the Hertzsprung-Russell diagram. This equilibrium, although transient, lasts long enough to constitute a significant stage in the evolution of a Sun-like star. On this horizontal segment, the core fuses helium into carbon and oxygen. The expansion is slowed because the pressure produced by the triple alpha fusion supports the upper layers, maintaining an overall calm state. Mass loss through stellar winds persists, but remains moderate, and the flash is already a thing of the past. Even though it lasted a moment on a cosmic scale, it was enough to reorganize the core and make helium the main fuel. This stage is referred to as the critical fusion point because of the sudden rupture of equilibrium caused by the degenerate state of the helium core. The analogy of a pressure cooker is telling. As long as the pressure doesn't exceed a threshold, nothing changes, but once crossed, all the energy is released at once. In the star, degeneration plays the role of the lid, and the heat from fusion that of the steam. After this surge, the star gradually absorbs the released energy. Internal reorganization leads to a slight contraction of the overall radius and an increase in surface temperature, the external layers heat up and readjust, leading to a new stable state. For the Sun, the horizontal branch phase could last about 100 million years. During this time, it functions like a stable fusion machine, but the helium will eventually be exhausted. For the planets, the helium flash has no major immediate effect. The mass loss is not rapid enough to severely disrupt their orbits. Significant changes will come later as stellar evolution unfolds. This episode is crucial. It transforms the core helium into the main source of nuclear energy and ends the degeneration. The radius decreases, the surface temperature increases, and the star settles on the horizontal branch. The paradox of this flash lies in its internal violence and its external invisibility. The opaque layers trap the energy, and only the gradual adjustments in size and luminosity betray the central upheaval. Astrophysical models confirm that for stars like the Sun, only a brutal impulse allows the helium fusion threshold to be crossed. The neutrinos produced during the flash are too fleeting and discrete to be easily detected from the outside. This critical fusion point marks the end of the degenerate core and inaugurates a stable phase where helium fusion creates carbon and oxygen. It is an essential step in the cosmic matter cycle, a prelude to their future dispersion in space. Thus, the helium flash, brief but decisive, embodies the complexity and power of stellar mechanisms. By freeing the core from degeneration and paving the way for more sophisticated fusion, it inaugurates a chapter of stability before the subsequent transformations that will guide the star towards the continuation of its cosmic destiny. As we reach this specific point in the Sun's long history, we enter a stage called the horizontal branch. This somewhat mysterious name comes from a particular type of graph, the Hertzsprung-Russell diagram, where stars cluster for a short time on a cosmic scale along an almost horizontal line when plotting their luminosity against their surface temperature. For our star, this phase begins about 6,100,000,000 years after its formation. It occurs shortly after a spectacular event, the helium flash, which marks the onset of the fusion of this element at the heart of the star. The Sun's interior then regains a temporary stability, offering a respite that, although short on a cosmic scale, remains considerable compared to a human lifetime. Astronomers speak of ephemeral calm, as it lasts only 100 million years, a modest fraction compared to the billions of years that have passed. Yet, during this time span, the Sun continues the fusion of helium, creating carbon and oxygen in its central regions, and triggers the exchange of matter, producing rarer elements. To understand why this stage is described as calm, we must return to what happens when the hydrogen at the core of a star like the Sun runs out. Before reaching the horizontal branch, our star experienced an energy crisis. The depletion of its central hydrogen required the ignition of helium as a new fuel. This transition is delicate. Helium fusion requires higher temperatures than hydrogen, and it can start abruptly if the material is highly compressed and has become rigid. When this fusion begins suddenly, specialists speak of a helium flash. In the case of the Sun, it's after this brief internal episode that the tranquility of the horizontal branch sets in. The star then reaches a new equilibrium. The stable fusion of helium produces carbon and oxygen, while temperature and pressure are maintained at a level allowing these nuclear reactions to proceed continuously and orderly. During this period, the size of the Sun decreases compared to the previous red giant phase. Before the flash, it had swelled spectacularly, reaching an immense size and very high luminosity. After the internal rearrangement that follows the definitive ignition of helium fusion, its radius stabilizes around a value of about 10 times that we know today. This means it would occupy a much larger volume than at present, while remaining less expanded than at the peak of its red giant phase. This reduction is explained by the internal reorganization. The fusion of helium produces a more stable and less explosive energy, which limits the expansion of the outer layers. The luminosity also experiences a temporary drop. Before the horizontal branch, it had increased significantly, fueled by the fusion of hydrogen shells around a core almost devoid of this element. In this new phase, it decreases slightly, while remaining higher than that of the current Sun. On the Hertzsprung-Russell diagram, this decrease, associated with an increase in surface temperature, places the star in a more moderate zone than that of the red giants. To the eye of a hypothetical observer, the Sun would shine more brightly than today, yet it would move towards provisional stability. To grasp the full subtlety of this phase, one must observe what unfolds at the core of the star. When mainly fusing hydrogen, the Sun used the proton-proton chain, 4 hydrogen nuclei combined into a helium nucleus at over 10 million degrees, releasing energy. Now, the dominant reaction is the fusion of helium into carbon and oxygen, requiring a temperature of about 100 million degrees. This heat allows overcoming the Coulomb barrier, the repulsion between positively charged helium nuclei. The process, called triple alpha, involves assembling 3 alpha particles to form carbon. Under certain conditions, this carbon fuses with other alpha particles to yield oxygen. In the core of the Sun on the horizontal branch, these reactions occur without sudden violence. The envelope is stable, and the density of the core sustains this fusion over tens of millions of years. Simultaneously, mixing phenomena transport newly created elements to less deep areas. Convective movements and internal flows move certain rare elements, sometimes up to the surface. Among them, lithium holds a particular place. During this phase, small amounts of a specific isotope may appear. Fragile, it is destroyed if it gets too close to the burning areas, but some of it manages to remain in more temperate layers or rise to the surface thanks to internal mixing. The quantities produced are small, but they illustrate a star's ability to enrich its envelope at each crucial stage of its existence. The duration of this ephemeral calm is estimated to be around 100 million years for a star with the mass of the Sun. On a human scale, it's immense. On a stellar scale, it's brief, especially compared to the 4.5 billion years of stability assured by hydrogen combustion. This difference is explained by the rapidity of the triple alpha reactions at very high temperatures. Helium is consumed much faster than hydrogen was. The entirety of this central reserve will disappear in a century of millions of years, ending this phase of stability. To visualize the interior of the Sun on the horizontal branch, imagine a core where carbon and oxygen are born, surrounded by an envelope still containing helium and some residual hydrogen. In the upper layers, movements related to differences in temperature and density ensure the circulation of heat and elements. The pressure exerted by light and photons produced at the center balances the gravity that pulls matter inward. As long as this balance is maintained, the star retains its stability without abrupt contraction or uncontrolled expansion. This stability, however, is just a passage. The central helium is regularly transformed into carbon and oxygen, but will eventually run out. When this fuel is exhausted and the conditions no longer allow effective nuclear reactions at the center, the star will have to find a new energy equilibrium. This moment will mark the end of the horizontal branch. In the meantime, the sun is experiencing a period of calm. Its size is stable, its brightness high but measured, and its nuclear reactions maintain a constant mixing of matter. To compare the current surface temperature of the sun to what it will present on the horizontal branch, imagine that today this surface is around 5,800 degrees Celsius. During the horizontal branch, the active fusion of helium and the relative contraction of the envelope could vary this temperature by a few hundred or thousand degrees, either up or down, depending on the energy distribution. The core, heated by the fusion of helium, could reach or exceed 100 million degrees Celsius, while the surface would remain more moderate than at the red giant stage when the star was largely dilated. It is this combination of temperature and brightness that fixes the position of the star on the horizontal branch of the Hertzsprung-Russell diagram. During these 100 million years, stellar winds continue to blow. Less intense than in the later phases where the star will lose more mass, they still expel particles from the high solar atmosphere, electrons, protons, heavier nuclei. This flux can transport newly formed elements, like carbon or a particular isotope of lithium, which will gradually diffuse into interplanetary space. At this time, if Earth still exists in a recognizable form, it would receive a stellar wind, with a composition altered by the production of carbon, oxygen, and potential traces of lithium. Even without life to witness it, this breath would contribute to enriching the surrounding environment, while the gradual loss of solar mass could induce slight orbital shifts of the planets. This phenomenon, however, goes beyond the strict framework of the horizontal branch, simply illustrating that the sun will never be a static system. From an astrophysical perspective, this stage constitutes an ideal laboratory for understanding the fate of stars of comparable mass after the depletion of their central hydrogen. In the Milky Way, many stars are or have been at this stage, allowing astronomers to compare their observations, particularly in star clusters. One can clearly identify the exit from the main sequence toward the red giant stage, followed by a horizontal branch at a given level of luminosity, the signature of helium fusion. The position and extent of this branch provide information about the age of the clusters, since the initial mass of the stars determines the timing of their departure from the main sequence and the duration of their helium fusion. The study of these groups, whether open or globular, thus allows for the reconstruction of stellar evolution history. At this stage, helium has become the main fuel. With all central hydrogen gone, only a peripheral shell remains active. The helium fusion supports internal pressure that counterbalances gravity, maintains the envelope's equilibrium, and sets the luminosity, without the explosive intensity of the initial flash. It is a phase of remission. The star, having navigated the crisis, enjoys a relative stability for several tens of millions of years. Chemically, this period marks the intensive production of carbon and oxygen, essential materials for future complex molecules. Later dispersed into space, they will enrich interstellar clouds, planets, and potential future planetary systems. The horizontal branch thus represents a key moment when the star begins to create a chemical legacy destined to spread through the galaxy. This slow preparation over colossal timescales feeds the cosmic cycle of enrichment in heavy elements. During this 100 million years, the sun will remain bright and warm from afar, with estimated luminosity several tens of times that of today's. Less imposing than during a full red giant expansion, it might appear ordinary to a distant observer, but for those who know its history, it embodies survival after a major energy crisis. The convective zone, where matter circulates through ascending and descending movements, can then vary in depth. This mixing brings some fusion products to the surface, enriching the stellar atmosphere in rare isotopes. The density and temperature conditions specific to this phase alter the efficiency of these exchanges, influencing the observable chemical composition. The summary of this stage can be condensed into 4 points. Helium fusion establishes itself durably. Carbon and oxygen are formed in abundance. Luminosity remains high, but lower than that of the red giant, with a radius about 10 times greater than today. An internal mixing promotes the appearance of light elements like lithium. This apparent stability, however, masks a continuous consumption of central helium, which, once depleted, will trigger a new reorganization of the star. For a distant observer, no spectacular changes would be visible over millions of years. The color and luminosity would vary too little to be noticed. But in the incandescent core, a complex nuclear chemistry is already preparing the next chapter of stellar destiny. Thus, the horizontal branch appears as a bridge between the red giant and more tumultuous phases. Gravity and radiation pressure balance, convection stirs the elements, and helium burns slowly. The question remains as to how the star will react once this fuel is exhausted. Formation of new fusion shells, irregular pulsations. The answers will come later, after this long moment of calm. It is a precious respite, a fleeting balance between gravity and pressure, between old fuel and new. This period, although brief on the cosmic scale, plays a crucial role in the history of the Sun, shaping its future chemical signature and preparing the upcoming upheavals. Imagine a star that has already gone through several phases of its existence, having transitioned from a main sequence where it burned its central hydrogen to an evolving giant stage. We now find it in what scientists call the asymptotic giant branch, or AGB. This phase, which begins about 6.2 billion years after its birth, is characterized by intense brilliance and an enormous size. Its outer envelope expands significantly as a consequence of the presence of not one, but two distinct fusion layers, one rich in helium, the other in hydrogen, each producing energy through complex nuclear reactions. To grasp the significance of this double shell, it's important to understand that the core has already contracted, becoming a dense nucleus composed primarily of carbon and oxygen, formed during previous helium fusions. The central temperature and pressure are no longer sufficient to sustain the most intense reactions, so energy now comes from outer layers. A shell of burning hydrogen covers an area of helium that fuses intermittently. These cycles produce energy and luminosity variations, known as thermal pulses, typical of the AGB. These pulses, which range from a few decades to several 100,000 years, start with the sudden ignition of the helium shell, inflating the upper layers. The helium is then temporarily depleted before a new cycle begins. From the outside, the star's brightness can thus vary greatly. Its photosphere sometimes extends even further, cools slightly, and takes on a more pronounced red hue, signaling a giant star at an advanced stage. As the AGB phase progresses, the volume of the star increases considerably. It could reach nearly 200 solar radii, its visible surface extending to the current orbit of Earth. The extent of this expansion depends on the mass lost by the star. Strong stellar winds appear, ejecting gas and dust into interstellar space and gradually reducing its mass. These winds originate in the outer layers, where the temperature drops to a few thousand degrees, favoring the formation of dust grains composed of carbon, silicates, or other minerals. These particles, struck by the star's light, experience strong radiation pressure. Photons push them outward, carrying away the surrounding material. Thus, dust shells are born that envelop the star before escaping into space. These superwinds also play a crucial role in enriching the interstellar medium. The AGB phase hosts a nucleosynthesis process called S process for slow neutron capture, occurring in still hot inner layers. Existing atoms like iron or nickel capture neutrons successively, transforming into heavier elements, strontium, barium, lead. The winds then disperse these enriched elements, fueling galactic chemistry. This process is visualized as a series of slow captures. After each neutron absorbed, the atomic nucleus may stabilize through radioactive decay, creating a new element. With successive additions, isotopes get heavier and heavier. These atoms will one day participate in the formation of new stars, planets, and potentially life. At the center of the AGB star remains a core of carbon and oxygen, surrounded by a helium shell, fusing episodically, and an outer shell of continually burning hydrogen. This instability fuels thermal pulses that bring fusion products to the surface, a phenomenon known as dredge-up. It enriches the outer layers and changes the envelope's chemistry. When carbon reaches the surface in significant quantities, the star can become a carbon star, displaying an even deeper red. The increased abundance of heavy metals also changes its spectral signature. The AGB phase is thus marked by constant upheavals, both in its internal structure and external composition. Mass loss in this phase is spectacular. In a few 100,000 years, the star can eject more than a tenth of its mass. This rate, often around 10 to the -6 solar masses per year or more, fuels the formation of a circumstellar nebula detectable in infrared, with the dust re-emitting the received heat. This loss of mass also shapes the future of the star. While the core remains stable or contracts, the inflated envelope gradually detaches. The variations in luminosity, due to thermal pulsations, attest to this slow separation. The asymptotic red giant is then about to abandon its envelope, paving the way for later phases where its hot and dense core will be exposed. To understand the significance of this material diffusion, it is important to remember that the majority of elements heavier than helium are not from the Big Bang, but were born in the cores of successive generations of stars. Asymptotic red giants play a major role in this dispersion, their expanded envelope facilitating the expulsion of gas and dust. Oxygen, carbon, silicon, and many heavier elements thus spread into the surrounding space. Part of this material will one day serve as a chemical reserve for the birth of new planets and stars. This cosmic respiration, where the star exhales its compounds, sustains the galactic cycle of matter, which is why astronomers carefully study AGB stars in our Milky Way. The latest interferometric observations and infrared surveys conducted by space probes reveal the complexity of these winds. Sometimes, irregular bursts, fine jets, or spiral shapes are detected, possible signs of the influence of stellar companions or magnetic fields on the ejected matter. The speed of gas expansion varies greatly, ranging from a few kilometers per second to much higher values in extreme cases. This diversity of aspects depends on the initial mass of the star, its original chemical composition, and any gravitational interactions with nearby planets or other stars. Thus, the AGB phase marks a decisive moment when the star, at the end of its life, returns to the cosmos some of the elements it has forged or transformed. Through its powerful winds and nucleosynthesis processes, it sows the seeds of future stellar generations. Its colossal radius, which can reach nearly 200 solar radii, testifies to the extent of its expansion. Thermal pulsations, the alternating fusion of hydrogen and helium in distinct shells, and the formation of dust together compose a true cosmic ballet. Seen from the outside, the red giant alternates between cooler, reddish phases and periods of brightness accompanied by the ejection of matter. A cycle that prepares the final stage, the abandonment of its envelope, leaving behind only a glowing core. Such is the grandeur of an AGB giant in full metamorphosis. About 6.3 billion years after its formation, the Sun reaches a spectacular turning point in its existence. It has already gone through most of the red giant phases and is at a stage where its core, loaded with elements heavier than hydrogen, is surrounded by multiple fusion layers. The star is about to undergo a series of major instabilities, the terminal pulsations, accompanied by powerful superwinds. During this crucial phase, episodes of intense mass ejection shape its appearance and disperse large quantities of gas and dust into space. These events, brief on a cosmic scale but intense for the life of the star, provoke remarkable variations in luminosity and leave behind complex gaseous structures, heralding the future planetary nebula. To understand this phenomenon, it is important to know that the core of the Sun, at this advanced stage, no longer has enough hydrogen to maintain classical central fusion. Most of the energy now comes from helium fusion in an inner layer, and further out, from hydrogen fusion in a peripheral layer. This configuration promotes the appearance of episodic crises, called thermal pulses. Each pulse occurs when the helium layer reaches extreme conditions of temperature and pressure, suddenly releasing a large amount of energy. This overpressure locally inflates the material, and then gravity causes recontraction. These oscillations can last from a few hundred to a few thousand years. On an astronomical scale, it is a final dance of energy that shakes the star before its final shedding. With each pulse, the Sun's brightness can vary by several magnitudes. Magnitude is a logarithmic measurement of an object's apparent brightness, where 5 magnitudes correspond to a factor of 100 in luminous flux. A distant observer would notice that the red giant changes regularly in brightness, sometimes over a short period, indicating these thermal pulses. After each one, significant imbalances in the outer layers result in winds of exceptional intensity, the superwinds. These winds, much more powerful than those in the classic red giant phase, expel significant amounts of matter. During this period, the Sun could lose about 0.3 solar masses more, a significant portion of its remaining mass. Due to these gusts, the gaseous envelope gradually detaches in several waves synchronized with thermal pulses. The star thus empties its outer layers, forming an increasingly complex circumstellar environment around it. Depending on residual rotation, the possible presence of a magnetic field, and gravitational configuration, the ejected material can structure itself into concentric shells, irregular filaments, or bipolar shapes. Concentric structures result from the quasi-periodic repetition of pulses, each pulse ejecting a new gas bubble that expands around the star. Sometimes, the ejection is favored in 2 opposite directions, forming marked lobes and an elongated silhouette. This bipolar form appears when a rotation axis, a magnetic field, or a stellar companion disrupts the symmetry of the dying star. At the heart of these sometimes dense clouds of gas and dust, processes of photodissociation and ionization modify their chemical composition. Photodissociation breaks molecules into fragments with energetic photons. For example, a carbon monoxide molecule can split into carbon and oxygen atoms under intense light. Ionization removes electrons, transforming atoms into positive ions. These phenomena are fueled by the star's intense radiation and by collisions in the turbulent winds. Gradually, the chemical composition of the gas evolves, and various ions and molecules appear. As it expands, dust grains can condense, especially if heavy elements like carbon or silicon are present. These grains, heated by the star, re-emit in the infrared, revealing the nature of the molecules and the density of the medium. Thermal pulses are triggered when the helium fusing layer accumulates energy. This zone, above the dense core, reaches several tens of millions of degrees. The explosive fusion produces carbon and oxygen, releasing strong energy that rapidly inflates the concerned region. Once the pressure diminishes, the star reorganizes and partially contracts until the next pulse. This cycle of rising and releasing creates deep instability, visible through significant brightness variations and bursts of matter ejection. Brightness variations related to pulses can reach 4 to 5 magnitudes, or even more, transforming the red giant into a remarkable variable star for an outside observer. Simulations show that several successive pulses can occur over a few thousand years, each with its dynamics. Some pulses project sheets of gas at several tens of kilometers per second that catch up with previous shells. At the interface, shock waves compress the matter, favoring the formation of new molecules and solid grains. The result is a nebular ensemble of nested structures, constantly reshaped by the mechanics of the winds. The loss of about 0.3 solar masses is explained by the increasing fragility of the red giant, unable to retain its outer layers. The less surface mass it retains, the more gravity decreases, facilitating the escape of matter. The radiation pressure exerted by photons coming from the core pushes dust and gas out of the star. Each dust grain acts like a sail, capturing the luminous energy and moving away into space. On a large scale, this multitude of grains and atoms forms an intense flow, equivalent to several solar masses expelled during the last million years. Although this time span is long for humans, it remains very short compared to the billions of years of the sun's stability. The study of these winds allows us to estimate that the sun will enrich its environment with a variety of chemical elements. Carbon and nitrogen, abundant in the fusion layers, disperse to fertilize the future dense regions of interstellar gas. This mechanism, called stellar recycling, refers to the role of intermediate mass stars like our Sun, which increase the content of heavy elements in the galaxy. These elements incorporated into molecular clouds will play an essential role in the birth of new stars, rocky planets, and potentially life. Over time, the stellar structure evolves with the progressive decrease in the mass of the envelope. The mass loss modifies the gravitational interactions with the remaining planets, influencing their orbits in the expanded solar system. Despite these changes, the most striking event remains the evolution of the star itself. The superwinds mark the transition towards an exposed core. When the bulk of the outer layers is ejected, the sun will be nothing more than a hot and dense core, ready to become a white dwarf. But during this phase, the terminal pulsations constitute a remarkable spectacle, a final act before the birth of a planetary nebula. Visually, if a giant telescope could observe from trillions of kilometers away, it would see a star expanding and brightening, then dimming as wisps of gas escape. Energy measurements would reveal peaks associated with flares of fusion in the helium layer, while near-infrared images would show the progressive condensation of dust in the distant envelope. Each pulse would allow mapping of distinct layers, testifying to the dynamic history over several millennia. These layers would sometimes extend to regions where distant planets or icy objects, like those in the Kuiper Belt, evolve. The formation of bipolar structures offers another spectacle. The gases evacuated at the poles would move more rapidly, forming two opposite lobes. Between them, a denser ring could organize, shaped by the solar rotation or the influence of a stellar companion in an inclined orbit. This type of configuration is observed in other aging stars in the Milky Way, testifying to various evolutionary scenarios that enrich the final nebula. While these winds propel matter into the void, photodissociation and ionization transform the chemical components. In hot zones, hydrogen exists ionized, while at a distance, the temperature allows the formation of more stable molecules. Carbon combines with hydrogen to form hydrocarbons or graphite particles. In other regions, oxides appear if oxygen is present in sufficient quantity. This varied chemistry makes the expanding envelope a laboratory, mixing extreme physics and complex chemistry. Each pulse lasts a few centuries to a few millennia, but the complete sequence can extend over several 100,000 to millions of years, depending on the mass and internal conditions. In the end, the residual mass will be so low and the core so hot that the superwinds will cease. The helium layer will have been almost entirely consumed, and the hydrogen layer too thin to generate new bursts. From that moment, the star will begin its slow transformation into a white dwarf, with a compact core, surrounded by an increasingly translucent gaseous envelope. This envelope will soon be ionized by the intense radiation, forming a planetary nebula visible for a few tens of thousands of years, before the core begins its long cooling process. However, before this stage, the phase of terminal pulsations plays a key role for stellar matter and the solar system. Significant quantities of gas and dust are dispersed in the surroundings. The interplanetary space, expanded by the radiation of the red giant, receives this continuous flow of hot particles. The remaining planets, if they survived the expansion, see their orbits modified and evolve in a hostile environment, but rich in matter. For example, if Earth subsists, it would evolve in an unusual environment, strewn with dust falling intermittently, potentially causing cosmic collisions, depending on when it would be affected by the solar expansion. On the scientific front, observing stars analogous to this stage has helped understand the mechanism of thermal pulses and predict the superwinds of the Sun. Several stars, known as long-period variables or AGB stars, exhibit fluctuations in brightness and gas dust shells visible in infrared. These spectacular variations, detected over months or years, show that even on our scale, it is possible to identify signs of instability at the core of these stars. The superwinds also contribute to the galactic chemical dynamics. By enriching the interstellar medium with carbon, nitrogen, oxygen, and intermediate elements, the Sun becomes part of a perpetual cycle of matter. These elements will return to the gas clouds where new stars and planets will be born, continuing the cosmic story. The phase of terminal pulsations and superwinds represents the Sun's last offering to the universe, a flamboyant farewell redistributing its fuel and layers, transformed by fusion. This chaotic phase, nearing the end of the asymptotic giant branch, will end when the star has expelled enough mass to reveal its incandescent core. The brightness will persist thanks to the core's heat, but the large pulsations will cease. The external layers, too thin, will no longer be able to fuel new explosive cycles. What remains is a detached shell, illuminated by the ionizing radiation of the sun, which has become a proto-white dwarf. When this radiation reaches very high temperatures, the envelope will ignite, forming luminous gas arcs and rings. This phase of superwinds marks the grand finale of the red giant, a last brilliance, where matter jets in massive sheets. The luminosity fluctuates sharply, and chemistry shapes the budding nebula. About 6,350,000,000 years after the sun's birth, a fascinating and contrasting cosmic scene unfolds. The star's outer envelope gradually detaches, giving birth to a planetary nebula. To grasp this phenomenon, let's first imagine the star at this precise stage of its existence. It has already gone through several phases, the most recent of which resulted in profound internal upheavals and powerful thermal pulsations, marking the end of its giant life. Now, its structure is transforming differently. The core, having become very hot and dense, is soon exposed to the cosmos, while the outer layers disperse. Let's start by defining the planetary nebula. Despite its misleading name, it has no link to a solid and habitable planet. This term comes from the circular and luminous appearance these objects offered to early telescopes, reminiscent of a planet's blurry silhouette. In reality, it is a cloud of gas and dust expelled by an aging star in the last moments of its active life. The luminous part forms a vast expanding veil, heated and ionized by intense radiation that strips electrons from atoms, giving it a particular clarity in space. This phase is short on an astronomical scale, lasting barely more than 20,000 years. This period may seem long for a human life, but compared to billions of years of stellar existence, it's just a flash. The trigger for this planetary nebula is the rapid rise in temperature of the exposed core. During the asymptotic giant branch, the star was surrounded by a thick layer of hot gas and abundant dust. Internal thermal pulses gradually expelled more and more matter, causing mass loss via powerful stellar winds, a continuous flow of particles torn from its surface. This gas spreads around the star. Simultaneously, the core continues its evolution. The nuclear fuel reserves deplete in the core and fusion envelopes. The internal structure changes dramatically, causing a spectacular rise in central temperature. When the envelope thins, a large share of this previously confined heat can escape outward. At this stage, the surface of the incandescent core, now exposed, often exceeds 29,700 degrees Celsius, sometimes approaching 30,000 degrees. This intense heat radiates into space in the form of powerful ultraviolet radiation, an invisible but highly energetic light. This radiation effectively ionizes the surrounding gas by stripping its electrons, giving it an electric charge. A highly ionized gas becomes luminous. This is what makes planetary nebulae shine, often with bright colors visible through telescopes from Earth. The transformation of the gaseous cocoon into a planetary nebula is manifested by sometimes astonishing shapes. A bright ring is often observed, a sort of luminous bubble around the core. Other times, wide hourglass-shaped lobes or very thin jets escape in opposite directions. Sometimes, magnetic fields or the presence of a companion star sculpt more complex structures, like twisted jets or bipolar shapes. Each star, depending on its mass, rotation, and environment, creates a unique nebula of almost artistic beauty, a testament to the richness of the cosmos. This phenomenon lasts about 20,000 years, a brief moment on a stellar scale. During this time, the envelope drifts into interstellar space, propelled by radiation and residual winds. The core, composed mainly of carbon and oxygen, remains behind as a fiery core. Without sustainable nuclear reactions, it radiates its heat before beginning a slow cooling, marking the end of the star's active life. Observing the nebular bubble, we admire the chemical elements that the star has synthesized and released over time: carbon, nitrogen, oxygen, and other heavier atoms. These elements, dispersed into space, will later enrich the gas clouds from which new stars and possibly new worlds will be born. These elements are essential to the chemistry of life. On Earth, life is based on carbon chains interacting with oxygen and nitrogen, as well as hydrogen. Carbon forms complex molecular structures, oxygen is involved in cellular respiration, and nitrogen contributes to protein formation. Without the continuous supply of these elements into the interstellar medium, it would be much more difficult to form life-friendly environments. Thus, planetary nebulae play a crucial role in the chemical enrichment of the galaxy. As they dissipate, they disperse these essential seeds, facilitating the birth of future stars and planets. Let us delve into the process of ionization of the gas by the core's heat. In astrophysics, to ionize means that an atom or molecule loses or gains electrons. Here, the loss of electrons is what matters. Ultraviolet radiation provides enough energy to extract these electrons, transforming the atom into a positive ion. A gas, rich in positive ions and free electrons, forms a plasma, which emits a particular light. Around a dying star, this plasma shines intensely in wavelengths detectable by astronomers. The colors observed in the nebula depend on the atoms present and their energy. Ionized oxygen, carbon, and hydrogen produce characteristic green, blue, or red hues. Over the 20,000 years, the nebula evolves. The material moves away from the core, possibly forming concentric shells or dispersing more or less symmetrically depending on the winds and currents. Collimated jets, when they appear, follow a particular axis, often due to a magnetic field or stable rotation of the star. In this case, the material exits through two opposite poles, creating bipolar shapes. Each nebula is unique. Some form an almost perfect disk, others a bubble, while others create complex shapes resembling a butterfly. These patterns tell the unique story of each star. During this process, the envelope continues to lose mass. The speed of gas expansion often reaches several tens of kilometers per second, which seems modest on a cosmic scale, but remains considerable if imagined on Earth. This expansion dissipates the envelope into space. Gradually, the density decreases. The star's light still illuminates the gas for a while, then the luminosity diminishes, and the gas merges with the interstellar medium. Eventually, no visible trace remains, except for the white dwarf, a compact residue at the nebula's core, and rare filaments of dispersed chemical elements. The planetary nebula phase also reveals the essential structure of the core that has become a pre-white dwarf. This white dwarf is a compact star, about the size of a planet like Earth, but with a mass comparable to that of the Sun. Its density is extreme, maintained by the pressure exerted by electrons. This final stage will be studied later. For now, the still very hot surface emits a large amount of ultraviolet rays, which illuminate the surrounding gas, forming a bubble rich in carbon, nitrogen, and oxygen. These nebulae are sometimes compared to celestial lanterns. temporarily lighting up the interstellar space. The chemical composition of the released shells is crucial for stellar evolution. During the previous phases, nuclear reactions in the inner layers transformed hydrogen into helium, then into carbon and oxygen. Sometimes, heavier elements are produced. Convection and mixing bring these elements back to the outer layers. Stellar winds and pulsations expel some of this material into space. That is why a planetary nebula contains carbon, nitrogen, oxygen, and other rare atoms. This enrichment is essential to the chemical diversity of the galaxy. To imagine this recycling, think of interstellar matter as a vast ocean where several stellar rivers flow. One comes from a supernova, another from the gentle death of an intermediate star expelling its shell in a planetary nebula, yet another from the evaporation of stars or cosmic collisions. These contributions mix, forming molecular clouds where new stars are born. The atoms from the dying sun may be used hundreds of millions of years later to form other stars and possibly habitable planets. This idea that we are made of stardust is not just poetic imagery, it's a scientific fact. Planetary nebulae have long been studied by astronomers to understand the final moments of stellar life. Modern instruments detect their emissions in visible, infrared, and ultraviolet light. These observations measure the expansion speed, temperature, and specific chemical signatures. Light spectra reveal emission lines characteristic of oxygen, nitrogen, carbon, or ionized hydrogen. With these data, researchers estimate the ejected mass, the cooling rate of the core, and the internal processes of the star. On Earth, if humanity still exists at this distant time, it probably could not survive the environment transformed by the sun's red giant phase. However, an adapted civilization or one located elsewhere could witness this breathtaking spectacle, visible perhaps to the naked eye or with powerful instruments. The luminosity of the shell would depend on the amount of ejected matter, its density, and the core temperature. The shapes and dynamics of the expansion would make these observations captivating over years, even though these changes remain slow compared to our daily rhythm. The ephemeral aspect of the planetary nebula, about 20,000 years, can be surprising given its vastness, since the cloud can reach several light years. In the almost empty space, the gas encounters little resistance and can dilute while maintaining its coherence for millennia, thanks to the energy released by the stellar core. When the temperature of the future white dwarf drops and the ultraviolet rays are no longer sufficient to maintain ionization, the gas ceases to glow. It becomes a thin mixture of wandering particles in the galaxy, blending into its environment. The former sun then remains in the form of a white dwarf, initially bright, then slowly dimming over time, carrying the memory of its past glory. Beyond the beauty and final destiny, the formation of a planetary nebula highlights the key role of intermediate mass stars in the distribution of chemical elements. These final phases, less spectacular than a supernova, are nonetheless crucial for providing the galaxy with some of its materials. The carbon, nitrogen, and oxygen released will serve to create complex compounds. Without this renewal, interstellar clouds would become impoverished, making it more challenging to form complex molecules and environments conducive to life. The term recycling is central. This phase of a planetary nebula is a natural cycle of galactic chemistry. When our sun reaches this stage, it reproduces a process already experienced by thousands of similar stars. Thus, the Milky Way is dotted with planetary nebulae, some of which are famous like the Lyrae Nebula or the Dumbbell Nebula, observed since the 18th century. Each tells a unique story, but all are based on the same principle. A hot, stellar core illuminates an expelled gas cloud. This scenario carries a profound poetry. The death of a star is adorned with a rare chromatic splendor, mixing beauty and chemical importance. Scientifically, this phenomenon reveals the internal nuclear reactions and the evolution of the Sun. From a reactor fusing hydrogen into helium, it becomes a heated core, releasing its heat through thin layers. For an observer, witnessing this nebula is to dive into times beyond the reach of our daily life. Temporal astronomers could thus observe, in a few millennia, a galactic spectacle where colors and shapes slowly evolve. Then the nebula would extinguish, leaving a dense, small, but massive core, while the traces of the shell would dissipate into the interstellar medium. When the star, close to the Sun, reaches the end of its advanced red giant phase, it releases its outer layers into space, revealing a hot core of extreme density. This is the beginning of the birth of the white dwarf, also called the post-asymptotic giant branch phase. To understand, one must imagine this star stripped of its envelope. During previous stages, the star has burned hydrogen and then helium until most of the central nuclear reactions have died out. At the end of this evolution, most of the fusible light matter is exhausted, leaving a core composed mainly of carbon and oxygen. This core is stabilized not by a classic thermal pressure, but by electron degeneracy pressure. This concept, although complex, simply means that in an extremely dense environment, electrons are compressed to the point where they can no longer share the same quantum state. Quantum physics imposes a limit on how close electrons can be, generating a pressure independent of temperature. This phenomenon prevents the star's core from collapsing, despite the intense gravity compressing it. After the expulsion of the external layers, the star retains about 0.54 times the mass of the Sun, concentrated in a tiny volume. One of the most astonishing characteristics of the white dwarf is its radius, comparable to that of the Earth. Contrary to the preconceived idea of a massive star at the end of its life, this core has contracted to the point of measuring only a few thousand kilometers. One can imagine an ultra-dense core, as large as our planet, but weighing more than half of the Sun, stabilized by electron degeneracy pressure. The density of the white dwarf is beyond comprehension. 1 cubic centimeter weighs about a ton, or 1,000 kilograms. By comparison, a thimble would have the weight of a compact car. This extreme compression is due to gravity and creates a very exotic environment, impossible to replicate on Earth without the material disintegrating. Our knowledge, therefore, comes only from physics and luminous observation. The initial luminosity of the white dwarf is high, as its core remains very hot, with the surface reaching several tens of thousands of degrees. This heat produces intense radiation, even if the surface is small. No fusion process renews this energy. Neither hydrogen nor helium burns inside. The white dwarf only radiates its residual heat. This pure radiative cooling marks a gradual slowdown in luminosity, which decreases according to a specific law proportional to the inverse of time, raised to the power of 5/7. This relation, established by theory and observations, describes how the white dwarf loses its brightness. This evolution can be compared to an ember removed from the fire. Isolated, it stops receiving heat and slowly goes out. The white dwarf, much more complex, follows this principle of energy loss without new supply. The electron degeneracy pressure, essential for stability, differs from the classical behavior of gases. Usually, pressure depends on temperature. Heating a gas makes it expand, cooling it compresses it. Here, quantum rules limit the compression of electrons. As long as the mass of the white dwarf remains below the Chandrasekhar limit, about 1.4 times that of the Sun, this pressure prevents further collapse. The core, primarily composed of carbon and oxygen, may contain other elements in small proportions depending on the mass and history of the star. Fusion is halted because neither the density nor temperature suffices to restart this process. This situation is like an extinguished fire, with the still hot embers taking a long time to cool, producing a faint, lasting glow. The initial phase of the white dwarf is marked by intense luminosity, with surface temperatures that can exceed 100,000 degrees in some cases. The object remains detectable at great distances in the galaxy despite its small size. Then, it begins a slow decline in luminosity over billions of years, fulfilling its role as a stellar relic. This long period allows astronomers to estimate the age of the stellar populations where they are found. Over time, the temperature drops from several tens of thousands to a few thousand degrees Celsius, making the white dwarf less and less bright. This process no longer involves fusion, but rather the simple dissipation of residual heat, hence the term pure radiative cooling. All the energy is lost without being renewed. Astrophysical models and observations confirm this decline according to the mathematical law mentioned, validating our understanding of these objects. This law even serves to date star clusters by comparing the observed and predicted luminosity of white dwarfs, offering a valuable indicator of cosmic history. Unlike active stars, the white dwarf no longer produces energy through fusion because its core is too dense and devoid of light fuel. This stellar remnant is an energetically dead object that only radiates the previously accumulated heat. The end of the post-AGB phase is not accompanied by spectacular explosions, but by silent stability ensured by quantum pressure. The luminosity gradually decreases. The surface temperature follows this decline. The white dwarf then resembles a burning white ember, with cooling quick at first, then increasingly slow over billions of years until it becomes almost invisible. We can summarize this birth in a few points. A core of about 0.54 solar masses, a radius close to that of Earth, a staggering density of about 1 million grams per cubic centimeter, stability ensured by degeneracy pressure, and pure radiative cooling leading to a gradual decrease in luminosity over astronomical timescales. Visually, the white dwarf is initially very bright due to its high temperature, but its small size limits its total brightness, which is less than that of a fully fusing star. Some white dwarfs are among the hottest objects detected, although their overall energy remains modest. Their radiation decreases over time, changing their color to redder hues. The study of these objects in star clusters provides insights into the chronology of the universe. By comparing models and observations, one can estimate the age of these stellar groups and date the formation of white dwarfs, evidence that the universe has aged enough for these relics to have cooled. The intimate structure of the white dwarf is a sphere of carbon and oxygen with highly compressed electrons. A gradual crystallization can occur, ordering ions into lattice structures similar to crystals, while electrons form a confined quantum gas. This crystallization releases latent energy, temporarily slowing cooling and influencing the luminosity evolution curve. This birth does not signify a return to life, but a new phase of existence without major fusion. The white dwarf is the final remnant for most stars, whose initial mass is less than about 8 times that of the Sun, forming a dense carbon-oxygen shell surrounded by a thin residual atmosphere. The internal calm is due to the quantum nature of degeneracy pressure, which is independent of temperature. Despite the cooling, the radius remains stable, preventing further collapse. The surface temperature drops with the luminosity, while minimal traces of hydrogen or helium testify to the residual envelope. The post-AGB birth marks the transformation of the red giant into a modest nuclearly inert star, but dense and hot, ready to emit its heat over very long timescales. This energetic silence evokes a long old age, where only quantum laws dictate the final destiny of the star. Finally, this cooling takes billions of years until the white dwarf becomes almost invisible, a hypothesis known as a black dwarf, which has never been observed as the universe is not old enough. Once the post-AGB phase is over, the incandescent core is delivered to the cosmic vastness with no possibility of regenerating. After tumultuous stages, our Sun, having become a white dwarf, begins a long journey of cooling. At this stage, it no longer resembles the familiar star we know. It is a blazing core, composed mainly of carbon and oxygen, encased in an extremely dense envelope. Thermonuclear fusion has long since ceased, and only degeneracy pressure keeps this white dwarf in balance against its gravity. We are in an incredibly distant era, ranging from about 100 million years after its formation to 100 trillion years later. Time stretches on the cosmic scale, and the white dwarf lives a silent, cold existence, very different from the intense solar activity of yesteryear. To fully grasp this phase, one must imagine an object without a nuclear energy source, but still initially hot, with an initial internal temperature of several million degrees Celsius. During its formation, the white dwarf retains a large residual energy inherited from previous phases. Deprived of fusion reactions, the heat it contains dissipates gradually into space. Its surface initially maintains several tens of thousands of degrees, slowly decreasing over the ages. The emitted radiation diminishes as the temperature drops. Over hundreds of millions of years, this decline remains perceptible, though very slow on the human scale. This phenomenon is called cooling by radiation, meaning the star emits the heat it holds without receiving new energy. No fusion reignites. Over billions or even hundreds of billions of years, the white dwarf goes through successive stages of increasingly lower temperatures, eventually becoming an extremely discrete object. This progressive transition, spread over several orders of magnitude, will be explored step by step. The crystal often evokes the transparency and beauty of ice or diamond, but in a white dwarf, crystallization has a very particular meaning. Initially, the core is a dense plasma of carbon and oxygen, a state where electrons and atomic nuclei move freely under high temperatures and pressures without forming stable, neutral atoms. In this context, there is no solid, crystalline structure. The particles are highly agitated. As the white dwarf loses energy, its internal temperature decreases. When pressure and temperature reach a critical threshold, carbon and oxygen gradually organize themselves into a crystalline network. The ions adopt a regular arrangement, like marbles aligned in a stable pattern. A true phase change occurs, comparable to the crystallization of water, but under extreme pressure and temperature conditions. Despite very high internal temperatures, the matter becomes sufficiently cold to initiate this crystalline structure. This change of state is not trivial. When a material transitions from a liquid or nearly liquid state to a crystallized solid state, an energy called latent is released. This energy slows down the overall cooling. During this crystallization, the white dwarf goes through a phase where heat loss decreases, prolonging the duration of its radiation. If one were to observe this event from afar, one would notice a plateau in the decrease in luminosity related to crystallization. The core mostly solidifies, forming a huge block of carbon and oxygen, while the outer envelope remains warmer and continues to radiate gradually. Latent energy released during crystallization creates a peculiar distribution of internal temperatures. Solidification can cause slight movements of matter due to variations in density or chemical composition. Despite this, the overall structure remains stable. Without fusion, evolution consists of a long decline in temperature and luminosity. One can imagine a massive crystalline core surrounded by a warmer cooling layer. The heat diffused from the deep layers slowly dissipates into space. The central temperature drops, decreasing from several million to a few 100,000 degrees Celsius after billions of years. The surface, initially very hot, reaches a few thousand or even fewer degrees after tens or hundreds of billions of years. The current universe, about 13,800,000,000 years old, remains young compared to the future life of this white dwarf. No one has ever observed a white dwarf old enough to be almost entirely crystallized and near extinction. This stage is a theoretical projection supported by stellar physics. Some observations already suggest ancient partially crystallized white dwarfs, confirming the scientific consistency of this slow phenomenon. Even if the nearby planets have likely been destroyed or perturbed during previous phases, some farther ones might survive. When the white dwarf begins its long cooling phase, ancient gas giants, asteroids, or icy planets may still exist. These survivors would orbit around a star with diminishing radiation. The mass of the white dwarf remains stable, with most of the loss of matter having occurred earlier. However, the internal structure undergoes subtle changes, such as a modification of the internal quadrupolar moment, slightly affecting the gravitational field. This phenomenon can lead to minimal orbital adjustments over hundreds of billions of years, imperceptible over shorter timescales. At this time, the low temperature of the white dwarf is no longer sufficient to seriously heat a distant planet. Any form of life as we know it could not survive this extreme cold. Furthermore, gravitational perturbations, such as the passage of other stars, could cause orbital shifts or planetary ejections over colossal timescales. The remaining bodies would either form stable orbits or be slowly expelled from the system. Over the course of this millennial cooling, the white dwarf emits less and less radiation. After several tens of billions of years, its outer envelope glows faintly in visible light, with its residual energy manifesting mostly in infrared. The star becomes a very discrete point, less luminous than a star seen from Earth. Over time, this point eventually fades into darkness, emitting almost no more radiation. This cooling, sometimes called the slow agony of a white dwarf, is a natural phenomenon. The star, having lost all internal energy sources, gradually fades away in accordance with the laws of thermodynamics. This end is not sudden. It unfolds over such long durations that no form of life or civilization could observe it. It is an almost eternal process, leading to a cold death after a period far exceeding the current age of the universe. Scientists sometimes mention the black dwarf, a hypothetical star with no notable light. This notion remains theoretical, as the universe is not old enough to contain any. One would have to wait tens of trillions of years to reach this extreme cooling stage, well beyond any observable era. Crystallization shifts the evolutionary trajectory of the white dwarf. As soon as a significant portion of the carbon and oxygen plasma forms a crystalline network, the transition releases latent heat that partially offsets the cooling. Thus, the white dwarf has an additional energy reserve, slowing the overall temperature decline and maintaining greater radiation than in the absence of this phenomenon. This mechanism is not unique to white dwarfs. On Earth, latent heat is exhibited during phase transitions, such as the solidification of water. In astrophysics, it is essential to explain why some white dwarfs show a delay in their cooling. Indirect observations, notably the brightness in star clusters of various ages, confirm that internal crystallization must be considered in evolutionary models. It is difficult to comprehend a duration of 10 to the power of 14 years, a scale so distant from our daily life that intuition falters. If the current age of the universe were 1 second, then 10 to the power of 14 years would represent an interval 1,000 times longer than all of history condensed into this second, a temporal vertigo. In this distant future, the white dwarf will continue to emit faintly, its surface temperature declining to a few thousand, then hundreds of degrees Celsius, nearing temperatures close to the cosmic microwave background itself. This background, a relic of the Big Bang, also cools with the expansion of the universe, making the thermal difference increasingly slight, and the white dwarf's radiation increasingly subtle. At that time, the galaxy will likely undergo profound changes, cosmic collisions, stellar dispersion, pushing the white dwarf and its potential planets towards the galactic peripheries or intergalactic void. Nothing will remain of the star's past splendor, only an inert core, frozen in time, of unimaginable density. This journey takes far longer than a mere voyage over a few million years. It is an extravagant temporality, where the object reaches a quasi-eternity. When the temperature has sufficiently dropped, the white dwarf will be called a black dwarf. This term may be confusing, but it refers to a star so cold and dim that it emits almost no visible light, detectable only by a residual infrared radiation, and even then, in a limited time window. No black dwarf is known today, as existing white dwarfs are too young to have reached this state. The theory predicts a slow decline in brightness linked to the physical properties of the internal degenerate matter. After several tens of billions of years, the internal density stabilizes. The ionization of carbon and oxygen is maintained by electron degeneracy pressure. When the core is almost completely crystallized, only a slow thermal dissipation remains at the pace of solid body physics, with a minimal heat flow to the surface, lost in the dark space. Even after several hundreds of billions of years, the white dwarf never becomes completely cold because reaching absolute zero is impossible according to thermodynamics. The black dwarf asymptotically approaches this temperature without ever reaching it. Beyond 10 to the power of 14 years, the nearly invisible white dwarf would continue its silent existence in the corners of the cosmos. This perspective far exceeds any known duration. No more energy input, no more internal mechanism, only a long cosmic sleep ending in total shadow. Subsisting planets, if not expelled, would orbit around an almost black, cold point, undetectable by visible light. Today, astrophysicists study these final phases through extrapolations. The crystallization time, residual heat loss, formation of a frozen carbon and oxygen core, gradual decrease in brightness. Everything can be calculated with quantum mechanics equations, plasma statistical physics, and hypotheses about initial conditions. Uncertainties persist over the very long term, but the trend is solid. Trapped in a crystallized core, our former sun, in the form of a white dwarf, will glide towards this never-observed state of black dwarf. This vertiginous future illustrates the ultimate destiny of a modest star, which will have provided light and heat for billions of years before slowly extinguishing. In the immensity of time, beyond 10 to the power of 14 years, this star becomes a cold, discrete dust, wandering in an expanding cosmic void. Only a fictional eye, heir to an inconceivable future, could glimpse the faint glow of this deceased sun, become the faintest of stellar embers. In this very long phase, the sun, after all its transformations, cooling down, slow crystallization, slowing due to latent heat, reaches a state close to invisibility. It becomes a monument to cosmic patience, suspended in time. No more activity cycles, no significant light, nor spectacular phenomena, just an obscure sphere existing in almost absolute silence. This millennial cooling, spanning from 10 to the power of 8 to more than 10 to the power of 14 years, testifies to a harmony between quantum physics, thermodynamics, and stellar dynamics. The sun, with its initial energy and flamboyant beginnings, transforms into a star of perfect stability, blending into the anonymity of the cosmos. This is the natural conclusion of a cycle billions of years old, when the sun was still a fusion hotspot. In this vast future, a crystallized shell of carbon and oxygen, similar to a massive cosmic diamond, will prolong the memory of a star that was once the source of all life on Earth. Welcome to this final stage of our cosmic journey, a voyage to the farthest future of the solar system, as our sun completes its last moments of glory to become a discrete white dwarf. At this stage, it no longer shines brightly. Its luminosity, now weak, persists primarily due to the residual heat of its former giant core. Around this stellar remnant, the planets that have not been absorbed or ejected continue their course, but the apparent peace masks a large-scale gravitational tumult. The galactic environment is not an empty expanse. It is more like a vast ocean where billions of stars sail, each with its speed, gravitational field, and sometimes its own planetary systems. Over time, some of these stars can approach relatively closely to our solar system, still centered on the white dwarf the sun has become. Even if, on a human scale, these distances remain large, they can be small enough, in galactic terms, to exert notable gravitational disturbances on the orbiting bodies. To envision this simply, imagine a spinning top peacefully turning on a large table. An external observer passing nearby and giving light nudges could, sooner or later, topple the top or cause it to drift toward an edge. Similarly, a passing star, whether of average mass comparable to the sun or slightly more massive like a double star, can subtly alter the trajectories of the outer planets. For these distant planets, the gas or ice giants, Jupiter, Saturn, Uranus, and Neptune, or even the small bodies of the Kuiper Belt, the attraction of a passing star can impart enough energy to eject them far from the central white dwarf. They would then become orphan planets, wandering in interstellar space without light or solar heat. Another phenomenon linked to these very long-distance influences is galactic tides. The Milky Way, our galaxy, is not static. It undergoes gravitational variations due to its mass distribution, a thick disk of stars, a very dense central bulge, as well as a more tenuous halo of dark matter and ancient star clusters. Galactic tidal forces act like a vast invisible hand that slowly stretches and deforms the outer solar system. This phenomenon, diffuse but acting over several hundred billion years, operates like a current that slowly disassociates fragile structures. For an already fragile solar system, these tidal forces can cause orbital rearrangements or the ejection of planets or trans-Neptunian objects. Next, the probable dispersion of the large planets and the Kuiper Belt must be considered. The latter is a vast zone beyond Neptune, populated by numerous small icy bodies, a witness to the primitive formation of the solar system. When the Sun becomes a white dwarf, its gravitational field, weakened by mass loss via stellar winds and expelled envelopes, will retain these distant objects less firmly. Their orbits will become more vulnerable to disturbances. Over star encounters, some outer planets and frozen small bodies may be projected inward, break up near the white dwarf, or be expelled into the infinite space. Jupiter, Saturn, Uranus, and Neptune, our four giants, maintain their orbits through a delicate balance. When the mass of the Sun diminishes and external influences disturb these trajectories, the celestial dance will lose its regularity. Some planets could adopt more eccentric orbits, drawing elongated ellipses around the white dwarf. In extreme scenarios, gravitational collisions could lead to the ejection of a planet. After countless revolutions, the solar system could be completely broken up, empty of planets, or retain only a few giants wandering silently around this white sphere in thermal extinction. Let's discuss the place of the deceased Sun among the wandering white dwarfs. When the core of a solar mass star has exhausted its fuel, electron degeneracy pressure stabilizes this compact remnant, the white dwarf. This dense object, the size of Earth, concentrates a significant mass, though reduced by previous losses. Throughout the galaxy, countless similar stars follow this same fate, swelling into giants, passing through unstable phases, then ending as white dwarfs. Over time, these remnants will disperse, influenced by the differential movements of the Milky Way, forming a mobile population in the galactic disk and the surrounding halo. The Sun, having become a white dwarf, will thus follow the galactic movement, completing orbits around the center, while participating in the chaotic dynamics of stars. After an immense amount of time, it will move away from its current position. Without direct collisions, rare in the vastness of space, the multiple close encounters, perturbations, and tidal forces will alter its trajectory. One day, on an immense timescale, its former place will be a memory, while the white dwarf drifts among other stellar remnants. In this journey, it will be part of a vast population of extinguished stars, destined for a gradual cooling until becoming, in an unimaginable future, hypothetical black dwarfs devoid of any glow. This phase remains theoretical, as the universe is not yet old enough to have observed it. Finally, let's mention the possible cosmic merger between the Milky Way and the Andromeda Galaxy. Galaxies are not static. They evolve, move, and sometimes collide. This encounter is promised to the Milky Way in several billion years. Slowly, the two galaxies approach until they merge. To visualize this phenomenon, imagine two clouds of smoke drifting towards each other. Upon contact, some wisps intertwine, others continue or dissipate. At the end of the process, a larger and more extensive cloud results, combining the initial elements. The stars themselves almost never collide directly, but the whole wraps, mixes, drawing spectacular loops of gas, dust, and stars. This merger triggers the birth of new stellar regions, reorganizes galactic orbits, and results in a single entity, often named Milkomeda, a poetic blend of the names Milky Way and Andromeda. In this reorganization, the Sun will have little chance of a direct collision with another star. Its orbit, however, will be reshaped by enormous gravitational forces. Simulations and calculations indicate that even if our solar system is not drawn toward the galactic core, it could migrate to a more extensive galactic halo. This sparsely populated region envelops the spiral galaxy, containing ancient populations of stars, globular clusters, dark matter, and hosting white dwarfs from disrupted systems. Thus, billions of years after the merger, our Sun, silent and reduced to a white dot, would float at the heart of this reorganized halo, far from its birthplace. Perhaps one or two surviving planets would persist, orbiting in the sidereal dark, occasionally crossed by a wandering comet. Meanwhile, the universe continues to expand, and its structures become more complex, with mergers and chaotic events. Galaxies also undergo the influence of large cosmic structures, clusters, and superclusters, as well as dark energy that accelerates the expansion of the universe. Imagining the fate of the Sun, one must keep in mind that the sky, already speckled with similar white dwarfs, will proliferate with new orphan planets, expelled objects wandering in the darkness, silent remnants of a once living system. On even longer scales, some cosmologists envision the ultimate evaporation of galaxies or the dissolution of all gravitational structures, although these hypotheses remain difficult to confirm. A major aspect of this narrative is the very wandering of the Sun turned white dwarf. Its faint glow will diminish over colossal durations. Deprived of nuclear fusion, it only radiates inherited heat. A slow process of internal crystallization, transforming carbon and oxygen matter, releases latent heat and delays cooling. On a cosmic scale, this thermal survival will extinguish. One day, the solar white dwarf will become a dark sphere, a hypothetical black dwarf. Even if this phase remains theoretical, it outlines the ultimate trajectory of our star in the cosmic night. Finally, the final dispersion. The supergalaxy born from continuous merging evolves over hundreds of billions of years. The stellar environment becomes sparse between isolated stars and remnants. Encounter after encounter, the solar captive objects will inevitably be separated, whether they are gas giants or dust. These gravitational collisions, even rare, accumulate over times where thousands or millions of years appear fleeting. Gradually, the long moribund solar system will melt into this turmoil. If observed from Earth, long gone, one might perceive the galactic parallax of this moving white dwarf. It is fascinating to understand that the disappearance of our solar system will not be a sudden event, but a diffuse, spread-out process, almost imperceptible. punctuated only by a few major unpredictable shocks. The essence lies in the slow release of the planets, the thermal death of the white dwarf, and the long-term galactic fusion. Paradoxically, while everything seems doomed to dissolution, the universe constantly reorganizes. Materials resulting from stellar nucleosynthesis, carbon, oxygen, iron, silicon, enrich the interstellar medium, allowing the birth of new stars and planets. For our Sun, already a white dwarf after shedding its upper layers, most of these elements have been propagated. No stellar life awaits it anymore. In this grand scheme, the question arises, would the ejected planets become wandering worlds capable of harboring any traces of frozen or fossilized life? For Earth, habitability will have disappeared long before this ultimate stage, as the red giant phase will probably destroy or transform the planet. However, in the speculative hypothesis that natural satellites of gas giants survive, still warm microenvironments might exist, heated by internal tidal effects. These scenarios lean more towards science fiction, as most orbital systems would be altered by successive disturbances. More broadly, what will remain of the legacy of this ancient star once disturbances, galactic tides, and merging with Andromeda dissipate the last planetary remnants? In the long term, the deceased sun will be just a fragment among a flow of wandering stellar objects. Its glow will slowly fade, while galactic structures continue to reorder. Within the reformed stellar halo, it will remain a trace of the past, like a grain of dust in a cosmic desert. Perhaps highly advanced civilizations, if they exist in such an aged universe, will, by studying these remnants, retrace their history. They will realize that this white dwarf has not always sojourned far from the galactic center, that it comes from a corner of the ancient Milky Way, and that it once bore the glory of a solar system rich in planets. The fate of the Sun and its system illustrates the relentless sequence of astrophysical processes that govern the life and death of stars. From the collapse of a cloud of gas and dust to the main sequence, the agony as a red giant, the transformation into a white dwarf, and the slow gravitational dispersion, each stage is part of a larger cycle of renewal in the galaxy. Nothing is lost. What escapes one object enriches another system or floats for eternity. Over hundreds of billions of years, encounters and tides create a vast mixing, and the white dwarf resulting from our sun will become an anonymous member among billions alike. The merger between the Milky Way and Andromeda is expected in about 5 to 10 billion years. This immense range marks only the beginning of a mixing that will last much longer. Meanwhile, the white dwarf will continue its revolutions in the new galaxy, modulated by gravitational interactions. Eventually, the solar remnant will be located in a restructured halo, unless pushed away or drawn closer to the galactic center by other encounters.